Work and energy. This discussion will include energy conservation. Kinetic energy, and we'll restrict our discussion here to the kinetic energy of translation, is energy of motion. Realize if something is spinning, such as the Earth, there is motion, and there is a kinetic energy of rotation. That is reserved for a future video. The equation for the kinetic energy of translation is 1/2 mv squared. And energy is a scalar. It does not have direction. Energy is conserved, but it can be converted from one form to another. Potential energy is given by the potential energy equals mgh. This is the potential energy with respect to gravity. This is the amount of kinetic energy that would exist if the object possessing the potential energy were to fall to the ground. In other words, if I have something elevated and it's not free to fall, either it's on a mountain or something, or maybe I'm just holding it, and I release it, it's going to go to the ground, and it's going to accelerate on the way. How much kinetic energy will it have when it reaches the ground? And that's potential energy. So we're going to look at the rock falling from a cliff scenario. A cliff is 40 meters high. What speed does it reach? What speed does it reach the ground? This rock that falls. So to answer that question, we consider the potential energy the rock has, mgh, and I'll just leave m alone and write 9.8 for g meters per second square, and h, the height is 40 meters. The ground height is 0, so the potential energy goes to 0. So we start with potential energy, and it is converted to something. The something is kinetic energy. The rock speeds up as it goes down, and that equation is 1/2 mv squared. So we had 0 kinetic energy at the top of the cliff, and all potential energy, and we go to potential energy at the bottom and all kinetic energy. Well, if energy is conserved, and we're ignoring friction, because friction will convert some of the energy to heat while slowing the object down, mgh equals 1/2 mv squared. And here the mass cancel. This is why a heavy object and a lighter object fall at the same rate. The mass actually cancels from the equation. 2 times 9.8 meters per second squared times 40 meters is v squared. So we'll take the square root of each side, and when we do, we're going to find out that this multiplies to 784 meters per second, because we had meters squared over seconds squared. We took the square root of the units just like we do with the number. And the square root of 784 happens to be 28. So we come up with a nice answer. That won't always happen. Well, scientists quickly realized there was a need to discuss change in energy. Not in the sense energy is being created or even destroyed, but in the sense that one form of energy is changing. If I lift a 10-kilogram object to a height of 4 meters, I do add potential energy. Perhaps I am interested only in how much energy the lifted object obtained. Well, this led scientists to come up with the concept of work. Work is actually the change in energy. It's equal to the dot product of the force multiplied by the displacement. Now, the dot product gives us the scale, and this is the amount of force in the direction of the displacement times the direct displacement. If there's time dependence on the force and displacement, we would have to go to calculus and write the work equals the integral along the path that the force takes, force ds. But if you're unfamiliar with calculus, just concentrate on this. It's a pretty good approximation for work, and that's good in most cases. Example, how much work does it take to lift an object of mass m to a height h? The force is what is needed to overcome the force of gravity. Think of moving an object upward with a force equal to gravity, so it will move very slowly. And kinetic energy will not be a consideration. Now, if you got the object moving when you get it up there, it's got another kind of energy, kinetic energy. We're thinking about the object just being brought up and stopped. The force needed is mg, or weight. That's what we have to overcome. The displacement is the height. How high did I have to lift the object? So the work in raising an object is mg, the force, times h, the height, which is the amount of potential energy the object obtains. That has to come from somewhere. I have to provide some kind of energy to lift the object. The other concept that would complete the discussion is power. Power is the amount of work done per time. So it's work divided by time. In other words, it's how much work you've done, how much energy you've changed, but divided by time. So the larger the value of time, the slower one does the job, the smaller the fraction, so power is reduced. So a small time gives me more power because it makes the fraction larger.